one of our collaborators, which is mine. Okay, so let's see one of the maybe most important application of this law, which is financial in finance. Let's start with the problem that we have done. So we have an order bookkeeping for high frequency trading. So what is an order book? An order book is a book which keeps tracks of buyers and sellers for a set of financial instruments or stocks. Whereas high frequency trading means that this kind of trades occurs at high speed with high turnover rates, high order-to-order trade ratios, and high frequency financial data. To give you a feeling, we are dealing with a fraction of milliseconds to give a complete answer for the data that we are analyzing. So let's go on. So this is kind of the trades flow which are ongoing, and we have to convert them in some kind of data structures. In particular, we have been assigned to reinterpret the data structures here, but the problem was also is also more difficult due to the fact that we didn't have only to store data accordingly, but we had also to judge and to evaluate trades. Indeed, on top of this storing and analysis, we had to evaluating a sort of metric which is important, which depends on the history of the trades themselves. And this was actually quite an issue. So let me start with the outline. So we will talk about the data which have been simulated for this part of for this problem. Then we will talk about the profiling of the codes, which means the analysis of the particular routines and the targets needed for each routines. Then we'll talk about the optimization, and finally we will have results and conclusion. So let me pass the pointer to Misha, which is talking about the data.
Okay, so as Nicola just mentioned, we had to optimize a code that takes some input data. So it's this button on top? Yes. And we thought, okay, let's first analyze we had to generate some input data, so we simulated the data, and then we had basically a matrix that had 3 columns. We have the 3 variables. We have the stocks, price levels, and exchange quantities. And as we have already mentioned, we didn't have any background in finance either, so you can just think of this as variable names. Okay, so we thought, okay, in order to optimize the code later on, maybe we can learn something from the data set. Let's investigate it. And so we did this, and we saw that, okay, we have like order of 1,000 different values in the stock variable, like 100 to 400 different price levels, and the exchange quantity is order of 10. So let's use these insights in order to constrain the data structure. That was our first approach. So then we did some further profiling. We used different profiling tools. We used gperf tools, we used wallgrind, and gprof. Gprof doesn't appear here because we couldn't get anything really useful out of it. So from gperf tools, we got this graph, which is called the call graph, where you can see exactly what functions in the code call which other functions, and you can also see like the percentages that are spent in each function. So this gives you a hint on where could you like start optimizing and where it's really where are the hotspots in the code. Okay, here in wallgrind, using callgrind, which is part of it, you can really go through the code line by line and see how much time is spent in each line of the code, such that you can one more time figure out a bit, more deeply where it's worth to start optimizing. Yeah, then we're really in the optimization part. I hand over to Tiziano.
Now, at the beginning, we were given a simple, let's say, naive implementation of this kind of bookkeeping. And it works as follows. What you have is, you have this kind of list here, which is all the stocks you get from the stock market here. And you, of course, want to have that sorted. I mean, you have identifiers for them, so to find them, you want them in a solid structure. So what we had there which is an associative sorted container. So it keeps the items sorted. And you can look them up by their ID. And the same also goes for the price level for each stock. So we have here a list of lists inserted here. And what's important here is that we don't want to keep price levels where there are no trades or where there are no stocks available anymore at those levels. So it consists basically of a find here in this structure, an insert if we don't find either the stock or the price level here, or then a delete if we really set the quantity of one price level to 0 to keep the structure small and to make the find faster. This is what was implemented, and this is what we also can see in the first benchmarks. And now what we did is we exploited some things here. As you've seen, the data, the IDs are rather limited to a certain size. So what you can do is you can exploit the fact that the price and the stocks are integers and think about directly creating a table and then using the price and the stock ID directly as index in that kind of table. Now what you have here is, you see here, we have to store zeros in that case. Yes, one big chunk of memory. But the find couldn't be faster, basically. So here we have to traverse this tree, and internally the map also has a tree to keep that list sorted. So here we have this log n complexity, and here we have, for the lookup, we have O1, really a constant lookup time, at the expense of memory, of course. We have to store zeros. And here what you can get for free, basically, is the lowest price. This is one of the metrics we had to work with to keep the lowest price in mind, but you might also track the highest price for a stock or the price level or whatever. And here you get basically an O1 complexity, where here you would have to start from the beginning and find the first entry where the quantity is not 0. So this is one thing we did. We optimized that array. We cached that lowest price and update it only if we remove it at some point. And all this is basically possible due to the profiling we saw. So it's obvious that we always have to find something in our structure, but the insert and the delete for the quantities are rather scarce, those events. So we thought that might be a good idea to take that bullet and really invest in optimizing the access time for it. Now, the problem when you do such a thing is you have to keep your complete address space small enough, otherwise you are wasting a lot of memory. And this is not only a waste of memory, but it also hurts your caching of the CPU. So when you have some kind of memory page swapped in the cache, and you have to jump to the end, for example, in your memory to get some value, then you're basically destroying your cache, and it gets hard to really prefetch data from the memory, and this getting data from the memory is always really expensive for a CPU. So what you do is, based on the assessment we made from the data, we really limit our address space. So it is enough to have IDs from 0 to 2048 in our example for mapping the stocks, and values go up to 8,192 for the prices. And the reason why there are basically powers of 2 is because then we can combine this all in one key. And if you know CPU architectures, the problem is that you don't have a two-dimensional array there, but you have one linear memory structure. So we are really interested in how to map this kind of keys onto your linear memory. So now we have two options. What you can do is you have this kind of decision to make. Do you want to have the faster or the memory which is closer together to be the prices, or should they be the stocks? And as you see further, it really makes a difference what you choose here. And it's also kind of surprising because it's not what you expect there. At least not entirely. Okay, when you now look at the matrix you get out of that you see that it is very, very sparse. So you have a lot of zeros, and as I said, this most likely is bad for caching values. So you have really to jump, the CPU really has to load the memory from different locations and has to jump around. And this is bad. And what you can do, as you would expect it also, that there is some, also from the data analysis dated, is that you have for each stock you have the lowest price, and from that you have a distribution. Is it also distribution from the lowest price? And up there you see that the events that you get higher prices basically there, or quotes for higher prices, get more salary. So you can really try to optimize by moving your data at the front. So for each stock, we save a lowest ever lowest price and move our data to the beginning, our price levels to the beginning. So we have, for each one we have an offset, and this makes it look like that. So we really put together, at least in this two-dimensional representation, put it together in one stride basically here at the beginning. And we hoped that this would help in optimization when we go for stock measure architecture of our data here. But I think we are now at the results, so you will see how that turned out.
Okay, now we can see that from the original code, which was the one with the previous 2000 millisecond time to get to our out of interest, we get to these optimizations codes, which are really cheaper with respect to the original one. We can see in particular that changing some little things. For example, from the first to the second one, we change how we look at the metrics, so changing the Meyer or stock Meyer or the price Meyer, and changing. And from the second to the third, we decrease the length of our memory, passing from 16 bits to 12 bits for the price, and we build another one which is more robust, and we have this different time for this code, but we are more or less on this side, in this order of magnitude for the time. And what we can see that we have different results with this shifting thing that we have done with our price levels. So if we keep in the no shift way, so the matrix really sparse, we got these results and this one. While if we shift all our data on the beginning of our matrix, we got these results. So it's not what we expected, because we thought that this should be the most fast one, and we still are investigating why this is going, and probably the shift is really expensive, or there are some reasons that we haven't understood yet, essentially. Anyway, we have tried even to store data in different way, from character to integer or 16 bits, and we have different times that are sometimes, well, they are always better for some particular examples, and in one it's the opposite, and we still have an algorithm in this kind of it's the opposite. But we got this result, which is really at 20 from 2000 milliseconds to 51 milliseconds, really a great improvement. We try to even understand which is the worst and the best iterations in our loop in terms of time, and using a clock, which is we think that this is not really the best one, because we got this kind of data. We have that the minimum iteration is really lower than the maximum runtime iteration, even if the minimum using this data is a little bit smaller, because probably our clock is getting more time to get the clock time when to get all when measuring the time. We are dealing with nanoseconds, so algorithm into two phases. A warm-up one, where we can find the minimum price for each stock, and then do the shift. We came up to this idea because watching data and we can see that the number of trades that we need to get to the lowest price are really almost 30 or 40, and we don't need all the after this number of iteration for that stock, we can assume that almost no other trades will be on lower price of the one that we got. So we can do the shift after this amount of iteration, and we want to get another shift during the rest of the algorithm. And after that moment, we will know even that the minimum will grow, the minimum instance that we won't get any other zero level between our minimum and the highest price that we get. There will be a displacement from the minimum, the real minimum, and the minimum considering the zero values, which will be at most of $10. So we can store really less data in our cache memory. So for example, a 10 dimension matrix for the price, and get using this information, we can use the normal thing in the warm-up phase, while using the shifted thing in the second phase of the algorithm. Other improvement that we can do is trying to understand better the character and the integer going well or badly somehow rottenness and why. And other things that we can do are, for example, giving an estimation of even the second minimum of each stock, of the level price of each stock. And using this technique, we can save times, giving the result immediately, and then after updating some data. And in this way, we can be even faster to giving the result that you asked. Other things that we can try is to improve the measurement of our iterations with some instruments and tools that are focused on catching the number of cycles that the CPU is doing, that are really asking the CPU to do this job and not are doing this work essentially. And that's it.
Okay, so first we want to hear the feedback from those that gave the topic. So maybe
yeah, so my first kind of impression is that I'm really impressed with the way you've approached the problem. So firstly, you've gone out of your way to sort of understand the problem, which you had no background in, and give yourselves a better definition of the background from my brief introduction. And then you've formulated the problem scientifically, and you've taken a scientific approach to the investigation of it. So I think more important than the outcome, which is nevertheless a very impressive outcome, and you've used many interesting techniques, and we can follow up on that later. But the approach to knowing what to measure, what to look at, what questions to ask, is really critical to success in this sort of when you're presented with this sort of problem. So for me, that's very impressive. I've got quite a few questions I want to follow up on, but I'll maybe do that afterwards.
okay.
Thanks.
Thank you. Well, good news, I guess. But maybe also from the other things, if you have questions, something you would have done differently. Yes, please.
Did you guys have a chance to look at playing around with different structures on how to store the data differently? Did you get any time to do that?
Well, other than this fixed size array and changing there, basically how the key is built, and moving the data around, we did not have time to investigate real other structures like directly use a tree or whatever.
Yeah. Cool.
Stefano, maybe we can get your comment also since you were the
of all, I was also very impressed by the approach you took to the whole problem, and we had a very interesting discussion about the whole thing. I wondered whether you had time to follow up a bit, as you mentioned some points, to have not only one core working on the actual implementation, but having somehow a hypervisor core on the other side that maybe updates these type of statistics that you were trying to use to sort the data better, and so on. I wonder whether you had time, because that was a very interesting idea.
No, we did not have time to do that, but we started basically the groundwork for the thing that I mentioned in the slides, this kind of maintenance work after giving the answer. This shifting of the prices, for example, this is done after we generated the sum, after we generate the metric. So to be fair, one should probably, when measuring the time, one should probably remove that part from the basic loop there, because the answer is already there. And this is what we understood is what they want, to have the shortest time to answer. And maybe after giving the answer, there's still time to do this kind of maintenance. And yeah, at that point, this could be also. But yeah, it's difficult to assess that.
Maybe I had one more question.
Oh, yeah.
I was kind of interested how you divided the work and how you interacted like between yourselves.
We were in the same room at the same time. That's already starting point, yeah, most of the time, for a really long time. And
that's important. As someone who runs a team spread across the world, I can testify to the importance of that.
And yes, I mean, and more or less the topics were exactly what we have shown at the beginning. So like data analysis, profiling of the code, and implementation optimization. And that's all. Of course, there was a lot of interaction among us, because nothing was really disconnected by the rest, because I mean, that's actually supposed to be. And yes, that's also we got this result, because we had lots of interaction.
Did you get a chance to play with optimization options of the compiler, or like when you were doing Valgrinder things, did you play with different?
Yes, I mean, when you do Valgrind basically, I mean, at least for the timings, it destroys almost every optimization you have there. I mean, there's really no point in doing real exact timing work or counting instructions or whatever when you do Valgrind. But it's interesting to see that when, for example, it's not only the compiler options to go to 03. I mean, we did at the beginning from going 0 to 03, over improves things, but you can still improve there when you, for example, really compile it for the architecture. This is the MArch native flag on the compiler. So you can get another 5% basically on this total runtime off when you really when you compile it to the architecture. So yeah, we're partially able to do that, but I must say we don't fully understand why we get those optimizations. I guess for that one we'd have to really look at the generated code and compare it and see. And maybe also gain insight from that on how to help the compiler better to optimize your code.
I think for now it is good, but we can follow up after the break, because we're on a tight schedule. So thank you very much.